In this video, we consider social cost-benefit analysis. Economists identify 4 different types of property regimes: private ownership, state ownership, common ownership, and open access. Private property gives the owner the right to utilize the property in any way that does not impose on others. In other words, it does not result in socially unacceptable spillovers. The owner benefits from use, from its exploitation, sale, conservation, and investment in improvements. This gives one confidence. Private property cannot exist, however, without state sanction and state protection. State ownership is where the state, the province, or federal government or state government owns the resource, but may give permission for others to use the resource, perhaps the land. Some examples include the cod fishery in eastern Canada, forest timber removals in British Columbia, or oil extraction in Alberta. The problem is, does the state really manage the resource for economic efficiency, or does it manage it for political goals or other goals? And of course, state ownership can deteriorate into another form, usually common ownership, which is ownership by a group or a community. It does have the ability to exclude others, and that's the key, and it's also the key difference between it, common property ownership, and state ownership. Members have specified rights and duties, and there is some means, some mechanism to allocate the land or resource use and share the benefits and costs. An example was Ethiopia's RISTI system prior to the 1975 land reforms. Currently in Ethiopia, all the land is owned by the state, although it has deteriorated somewhat, or maybe it's not known as deterioration, into common property. Common property is often recommended by many as a solution to fishery, forestry, and other resource exploitation in a variety of different jurisdictions. Open access is known as res nullius. It's a lack of property ownership. No ownership rights are allocated. This is what Hardin meant by the tragedy of the commons. Open access can result in destruction of the land or resource due to overexploitation, but that's not necessarily the case. It depends on the circumstances, whether those be economic or biological. Now, when we come to social cost-benefit analysis, we come to a particular set of criteria for comparing or judging projects. It's a specific form of project analysis. Basically, it adds up all of the social, economic gains and losses, the surpluses, and it employs discounting. The early history of cost-benefit analysis really started with the U.S. Flood Control Act of 1936 because it stated that it had to take into account, or in making a decision about a project, the project had to take into account the benefits to whomsoever they may accrue. These benefits had to exceed costs. In 1950, a Green Book was published by the Interagency Committee on Water Resources, now known as the Water Resources Council. In 1958, the Water Resources Council published a revised edition of the Green Book. As well, other cost-benefit analysis material became available, notably by McKeon and Otto Eckstein in 1958. Subsequently, of course, there was a lot of refinement in cost-benefit analysis with people like Ezra and Mishan and many others creating books on cost-benefit analysis. What are the assumptions of cost-benefit analysis? Well, the first assumption is that only marginal changes are valued. The distribution of income is given. There are no significant distortions in other markets. Tastes, income, and wealth of current generation are the starting point for desires and ability to pay of the future generation. In other words, the decisions are based on the distribution of income and incomes that are represented by the current generation. All individuals are treated equally. A margin of value, the marginal value of a dollar going to a rich person, is treated the same as if that dollar were to go to a poor person. Uncertainty is absent, or it's somehow handled using expectations, or it's handled in the discount rate. Now, there are a variety of criteria that can be employed. For example, we begin with the present value of costs. So we take the costs in every year, denoted CT, so that's the cost in year little t, and we discount it by this factor 1 plus r to the power t. So if r is 4%, then, and it's 10 years from now, then the discount factor would be 1.04 to the power 10. We do the same thing with benefits. We sum the benefits over time, but it's the discounted benefits, so we bring them to the present. We always need to bring everything either to the present value or the future value. If we were to go to the future value, then instead of dividing by this term, we would multiply by it. So we take the benefits in every year, discount them as to the year when they occur, and then sum that over the period of time, where t equals 0 is today. In other words, we assume the project begins today. Then the net present value is simply the present value of the benefits minus the present value of the costs, and if the present value of the benefits exceeds the present value of the costs, so that that is greater than or equal to 0, then the project may be worth undertaking. That does not mean that it is worth undertaking. And finally, we can take the ratio of the present value of benefits over the ratio of the present value of costs, and that has to be greater than or equal to 1. And you can see that these two are complementary. They give the same result in a way. Now, R here is the discount rate used, and it's a social rate of discount and not the private rate of discount that we discussed in an earlier video. Now, there's alternative ways to present the benefit-cost ratio. We could look at the benefits to cost of public funds by taking the present value of the benefits and subtracting the present value of the private costs and divide it by the present value of the public costs only. Or we can look at the benefit-cost ratio of the operating capital, where we take the present value of the benefits minus the present value of the operating and maintenance and replacement costs. So these are annual costs. And we divide that by this capital cost, the construction cost. Or we can look at the benefit-cost ratio of the project alone, which is the present value of the benefits minus the associated costs divided by the present value of the project cost. A good example of this was in irrigation, where the dam was built and we only looked at the value of building the dam without taking into account the irrigation costs. So, for example, in southern Saskatchewan, the Diefenbaker Dam was built with the idea of irrigating land. And when they calculated the benefits and costs, they took into account only the costs and benefits of bringing water from the lake, from the reservoir, to the farm. They did not take into account the fact that the farmer had to invest in equipment to produce the outcome, nor did they look at the benefits to the farmer. And it turned out that many of the farmers, in fact, just about all of the farmers, refused to use the water that was brought to their property because they would not make money. The benefits of the project for the farmer did not exceed the costs. Now, final criterion here is what is known as the internal rate of return, which we denote with a delta. And what it says is we set the net present value of a project equal to 0, and we find what that value is, what that delta is going to be. And the criterion is that delta has to be greater than or equal to R, where R is the opportunity cost rate of return, or the opportunity rate of return. Now, a useful way of, going back to this, one of the big problems is this T, because if you try to solve this, you're going to end up with an equation that has the possibility of multiple solutions for delta. And you have to choose one of those that makes the sense. That's one of the problems with determining this. However, it can be done. The bond formula is very useful for making calculations. And the bond formula tells you that the value of the bond V is equal to Y over R, where Y is the annual payment. So it's the amount that you get every year, assuming that that payment is constant from year to year. And V is the value of the bond. So it's a bond that gives you Y each year into perpetuity. So how do we derive the bond formula? Suppose you begin to receive Y dollars one period from now and then into perpetuity. What is that worth? So we begin by constructing this over a period of N years. And we find that Y divided by, so you get the Y next year and you divide that by 1 plus R, the discount rate. Plus you get Y 2 years from now, and you divide that by 1 plus R squared, and so on for N years. Then you multiply the left-hand side by 1 over 1 plus R, and you do the same on the right-hand side. So this Y over 1 plus R becomes Y over 1 plus R squared, and so on through. So you end up with Y divided by 1 plus R to the N plus 1. We subtract 2 from 1. So in other words, Vn minus 1 over 1 plus R to the Vn is equal to this term here that I have circled, Y over 1 plus R, minus these terms cancel. Okay, all the way through they cancel. And you're left with this term over here. And once you take out Y over 1 plus R, you get Y 1 minus 1 over 1 plus R to the power N. On the left-hand side, you get R over 1 plus R, so you multiply the right-hand side by 1 plus R over R, which will eliminate this 1 plus R term, and you get Y divided by R. This term here goes to 0 in the limit. As n approaches infinity, as n here goes to infinity, this goes to 0, so you're left with V equals Y over R. Is this useful? Well, it is. Suppose you receive $50 per year for 43 years. What is the present value given an interest rate of 5%? You can calculate the annual gain, add it to the principal, repeat for 43 years in Excel. Or you can use the bond formula. The value of the bond, if kept for an infinite time, is equal to Y over R, $50 over 0.05, where 0.05 is the interest rate. That gives you $1,000. The value of the bond after 43 years is given by this $1,000 minus $1,000 divided by 1 plus R to the 43, because in 43 years from now, it'll also be worth $1,000, but you don't get any more money after that, so you need to subtract that from the value of the bond. So you get 1,000 minus 1,000 over 1.05 to the 43, which then works out to $877.30. So as an assignment or as an exercise, you could try to use the bond formula and its derivation to write code that calculates how much you would need to pay monthly on a $650,000 mortgage. Now, the question is, what discount rate do we use? From a theoretical point of view, economists use what is called the Ramsey discounting formula, which distinguishes between the utility rate of discount, or we also can call that the social rate of time preference, or the intergenerational discount rate. So it distinguishes between let's just refer to it as the intergenerational discount rate, and the consumption rate of discount. We distinguish between the rate at which the utility is discounted, the welfare of future generations is discounted, and the rate for discounting our consumption. With a single consumption good, the Ramsey formula is simply delta T, where delta T is society's consumption discount rate at time T, equal to the utility rate of discount, alpha, the utility rate of discount, plus this epsilon, or eta, I guess it's epsilon, we'll call it epsilon, where GT is the rate of change in consumption, which is given by C prime T, which is dC dt, the per capita change, the change in per capita consumption with respect to time, weighted by the negative of the elasticity of the marginal utility of consumption. All right, so this is the negative of the elasticity of the marginal utility of consumption, which is given by this term here. It gets a little complicated, where U prime is the derivative of the utility with respect to consumption on a per capita basis, and U double prime is the second derivative of that, or the derivative of the marginal utility, which is the U prime, with respect to consumption. So elasticity tells us how fast the marginal utility of consumption, U prime, falls over time as consumption rises. So this GT, the rate of change in consumption, will change over time, and that will cause that discount rate to differ from one period to the next. The Ramsey formula says simply that society's consumption discount rate is equal to the social rate of time preference, or what we have called the intergenerational discount rate, plus the rate of change of consumption multiplied by the negative of the elasticity of the marginal utility of consumption. In essence, then, there are two discount rates to consider: the utility rate of discount and the consumption rate, or the consumption discount rate. So the Ramsey formula can be considered a prescriptive approach to discounting, with the parameters alpha and epsilon chosen on the basis of ethical deliberations, or it can be considered a descriptive approach to discounting, with the parameters alpha and epsilon based on market rates of return. In other words, decisions in financial markets. The value of the social rate of time preference, or the intergenerational rate, alpha, can be based on the real rate of return on long-term government bonds, while the consumption rate of discount, could be based on the rate of return on risk-free investments, the opportunity cost of capital, or the opportunity cost of funds, which we'll see in a minute. So what are the sources of funds to finance public projects? Well, increased public sector borrowing. It could displace an equal amount of private investment, and if it does, an appropriate rate to use then would be the private rate of return, which is probably around 7% to 8%. And this is known as the opportunity cost of capital rate. Funds could also be coming from income taxes, where an equal amount of consumption could be displaced. So then the consumption rate of interest, which is lower than the rate of return on capital investments, might be appropriately used, in which case we might think of the rate on savings being the appropriate rate. Now, the opportunity cost of funds, on the other hand, takes into account the fact that both borrowing or income taxes can be used at the same time. Suppose public investment project costs $100 and $40 displaces private investment and $60 displaces consumption. Suppose the rate of return to the private investment is 8% and the consumption rate of interest, or savings rate if you like, is 2%. Then the opportunity cost of fund is 0.4, 40 out of 100, times 8% plus 0.6, so 60 out of 100, times 2%, which gives a opportunity cost of funds of 4.4%. The difficulty in deriving the opportunity cost rate is determining where marginal funds originate. Do they originate with the private investment, or does it displace consumption? Further, there's a problem that not all government revenues come from income taxes or domestic borrowing. Governments earn income through charges, royalties on resource extraction, tariffs on imported goods, and many other places. So what discount rate is used in practice? Well, individual income tax rate of 50% implies a return to individuals of 4%. If we assume, of course, that they get 8% on bonds or whatever in the investment sector. So then 4% is the consumption rate of interest. The U.S. Office of Management and Budget uses a 7% rate to discount costs and benefits external to the government, but a 4% rate for costs and benefits internal to the government. The province of British Columbia officially required that a discount rate of 10% should be used in determining whether to make decisions. All right, so for resource investments. But I've never seen any studies that were using 10%. And this was, I last looked at this in the early 2000s. Streams of costs and benefits over time need to be compared in a single year, whether current or future, which implies that costs and benefits needed to be weighted. So we need to be able to discount. There's no getting around it. Outcomes of a cost-benefit analysis are very sensitive to the discount rate. So we have two other problems here, in that people have differing rates of time preference, and individuals even employ different discount rates for different circumstances. The rate used to discount future gains is about 3 times higher than the rate used to discount future losses. And this conclusion came out of a number of different studies that were done as experiments with people. People also discount future environmental benefits at a lower rate than future consumption benefits. In other words, they look at the environment as more important in the future compared to their own consumption. But when the future comes, it might turn around. They might then look at consumption and consider it as more valuable. So they tend to avoid very small risks of death from a nuclear or environmental disaster, but they're riding a motorcycle. People are willing to pay less for something if they don't own it than what they are willing to accept for the same thing if they do own it. And we see that in this graph here, all right, where a gain is valued by this much, but a loss is valued by that much. These two being equal. This is our loss, and this is the gain. And you see right away that the gain is valued in terms of utility by GE, and the loss is valued by EL. In other words, at that endowment point, all right, we're saying that the individual to give up that endowment would require a lot more than the person is willing to gain from that same kind of endowment. So in other words, indifference curves tend to be kinked. One study found that people would be willing to accept 6.89 vacation days in 2003 to give up 6 days in 2006. But we're only willing to pay 3.24 days to gain 6 days in 2006. So the willingness to accept this offer was much, much greater than the willingness to pay. But willingness to accept represents compensation demanded. So in a famous article, Daniel Kahneman and his colleague Amos Tversky argued that the value function of economists should be adjusted as V of x is equal to x for x greater than or equal to 0, but valued at lambda x if it was less than 0, where lambda x was greater than 1 and represented a loss aversion parameter. Then the question arises, do we consider a 0 discount rate? Well, it doesn't help future generation if it takes away from private sector investment. And the option is that the government can always invest in companies that generate 11 to 12% rates of return and then use the proceeds to pay for future programs. Do we adjust for inflation? Should the discount rate be adjusted to consider the potential for inflation? Some analysts make an adjustment for inflation, but this requires that they forecast what the future inflation would be. My view is that you should not place that burden on future inflation on the discount rate. You might want to adjust or raise the discount rate to account for risk and uncertainty, but even that's questionable. So my preference would be to use Monte Carlo simulation about the discount rate, or better yet, about the components of cost-benefit analysis that are risky or uncertain. For example, what are future output prices going to be? And use the Monte Carlo simulations, which would give you an average net present value or benefit cost ratio with some kind of distribution of that average. And that's where we're going to end